Hello dear students, my name is Venkatesh. Last class we discussed that valency bond theory in the coordination complexes. Now let us continue some examples of the coordination complexes according to valency bond theory. So now let us see the first example is nickel Cl4, nickel Cl4 minus 2. Nickel Cl4 minus 2, right? So I am writing here nickel Cl4 minus 2. Nickel Cl4 minus 2. So this is one of the coordination complex. So this coordination complex we have to identify the hybridization and geometry and spin multiplicity and magnetic moment you have to identify according to valency bond theory. So now here nickel is the central metal atom. According to valency bond theory, first step is identification of the central metal atom. So in this complex the central metal atom is nickel. So first step is identification of the central metal atom is completed. Second one, identify the oxidation state of the central metal atom. So what is the oxidation state of the central metal atom? Here 4 chlorines are present, -4, and here -2 is present. So finally the nickel will be +2. So central metal atom oxidation state is +2. So nickel oxidation state is what here? +2. So based on the oxidation state of the nickel, we have to find the electronic configuration. So nickel atomic number is 28. The electronic configuration of the nickel is 3d8 4s2. Now nickel losing the 2 electrons. Nickel losing the 2 electrons. 2 electrons losing nothing but the 2 electrons are losing from the valence shell. So now the electronic configuration of the nickel is 3d8, 4s0 and 4p0 because 4p shell also is present. So nickel oxidation what electronic comes is what here 3d8, 4s0 and 4p0, and 3d8 nothing but here 8 electrons are present in the 3d. So 3d having the 5 subshells here. So 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons are present here, and 4s is empty and 4p also empty. So now your nickel coordination number is what here? Nickel coordination number is 4 because 4 ligands are donating the 4 electron pair to the central metal atom. At the time coordination number of the nickel is 4. So according to valency bond theory, nickel coordination number is 4. That means it is makes the available empty orbitals are 4. According to valency bond theory, central metal atom it is makes the empty available orbitals. It is equal to its coordination number. So nickel coordination number is 4. It is makes the empty available orbitals are 4. So it is makes the empty available orbitals are 4. These 4 empty available orbitals are intermixed and it will be formed the 4 sp3 hybrid orbital. 4 sp3 hybrid orbital. To these 4 sp3 hybrid orbital, these 4 chlorines are donating the electron pair. At that time, so nickel to chlorine, 4 coordinate covalent parts are formed. Now let us see the hybridization and the remaining characters here. Hybridization, we know that the hybridization of this complex is sp3. So hybridization is sp3. Hybridization is what here? sp3 hybridization. After the hybridization, geometry. So if the hybridization is sp3, but the geometry of the complex, always the hybridization is sp3, the geometry of the complex is what here? Tetrahedral. So next one is after the geometry, you have to find the spin multiplicity. After geometry, you have to find the what? Spin multiplicity. So spin multiplicity. How can you find the spin multiplicity? Based on the number of unpaired electrons. Based on the number of unpaired electrons, the formula of the spin multiplicity is what? 2s plus 1. So number of unpaired electrons, how many? 2. Number of unpaired electrons, 2, nothing but spin character, how much here? Here plus of, totally 1. So s value is 1. At the time, 2 into 1 plus 1. So finally the spin multiplicity is how much here? 3. So next of all, magnetic moment. Okay, next one is what? Magnetic moment. So magnetic moment formula is what? Nu equal to root over n into n plus 2. Root over n into n plus 2. N nothing but what here? Number of unpaired electrons. N nothing but number of unpaired electrons. Then u equal to number of unpaired electrons, how many here? 2. Then 2 into 2 plus 2. 2 plus 2, 4. 4 into 2, 8. Then root 8 is the magnetic moment. So Bohr magnetic moment is what? Nu. Nu is the what? Root 8. So this is the what here? Hybridization is sp3. And next of all, geometry is tetrahedral, spin multiplicity is 3, and magnetic moment is root 8. And the nature of this complex is unpaired electrons present, so that's why it is paramagnetic in nature. It is which nature? Paramagnetic in nature. So this is hybridization, geometry, spin multiplicity, magnetic moment, and magnetic nature of this complex, right? So this is what nickel Cl4 and -2. So of this complex, what hybridization, geometry, and spin multiplicity. So let us see that another example. Okay, the another example is nickel CO4. So nickel and carbonyl group here CO4. Okay, this is the complex here. So here we have to identify. I am comparing the two here. Okay, one is nickel CO4 and one more is nickel cyanide. Okay, nickel cyanide 4. Nickel cyanide 4. So here two complexes I am writing here. One is nickel CO4 and another one is nickel cyanide 4. Okay, another one is what? Nickel cyanide 4. So for these two compounds, we have to find the what different characters according to valency bond theory. Right. So now see here nickel CO4 I am taking. What I am taking here? Nickel CO4. CO is what? A neutral ligand. Neutral ligand nothing but there is no oxidation state on the carbonyl group. Indirectly, the nickel also does not have any oxidation state. So that means nickel atomic number how much here? Nickel atomic number is 28. The electronic configuration of the nickel is 3D8 4s2. 3D8 4s2. There is no what electrons are losing because it is a neutral ligand. Carbonyl is a neutral ligand. Because of the nickel oxidation state is what here? 0. So that means nickel does not loses any electrons. So now let us see that write the electronic configuration here 3D8 4s2. Right. So now 3D8 4s2 I am writing here 3D. So D subshell how many electrons are present? 8 electrons are present here. 1 orbital, second orbital, third, fourth, 5 orbital, but 8 electrons are present. 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons are present. In 4s also 2 electrons are present. And 4p there is no electron. 4p there is no electrons are present. So 4p there is no electrons. Right. Now but here carbonyl group is what? Carbonyl group is the strong field ligand. Carbonyl group, cyanide groups are what? Strong field ligand. The primes are strong field ligand. Unpaired electrons will be paired. So here what happened? This is unpaired electron. These unpaired electrons are paired by whatever the electron present in the 4s. Now these 4s electrons are going to here and these unpaired electrons are going to be paired now. These unpaired electrons are what happened here? Paired. So now let us see that unpaired electrons are paired here. So 1, 2, 3, 4. So every orbital is filled with electrons. Now every orbital is what happening here? Filled with electrons. Now let us see here. S orbital is empty and 3 p orbitals also empty. S orbital is empty and 3 p orbitals also empty. Now the coordination number of the nickel how much here? 4 because each carbonyl group is donating 1 electron pair. At that time 4 carbonyl groups are donating 4 electron pair. Number of electron pairs donating by the ligands is equal to coordination number of the center metal atom. So center metal atom coordination number is 4 now. So according to valency bond theory, central metal atom makes the available empty orbitals is equal to its coordination number. So coordination number of the nickel is 4. It will make the 4 empty available orbital. These 4 empty available orbitals are intermixing and it will be formed. The hybridization is what? sp3. So based on these 4 empty orbitals, the hybridization of this complex is what? sp3. Hybridization sp3 nothing but the geometry of the molecule how much here? Tetrahedral. Now spin multiplicity. Spin multiplicity, what is the formula? 2s plus 1. S nothing but number of unpaired electron. Is any unpaired electron is there? No unpaired electron. That means 2 into 0 plus 1. The spin multiplicity value how much here? 1. Next of all magnetic moment. Magnetic moment, what is the formula? Root over n into n plus 2. N nothing but what? Number of unpaired electron. There is no unpaired electron. That means magnetic moment is what? 0. Next one, all are paired electron. That's why the magnetic nature is what here? Diamagnetic nature. Okay, the complex is which nature here? Diamagnetic nature. So this is what characters of the nickel CO4 according to valency bond theory. Let us come to here. So here cyanide also strong field ligand and cyanide is a negative ligand. Negative ligand nothing but here -4 and here -2. Finally the nickel oxidation state will be +2. Now I am writing the nickel oxidation state is +2. According to nickel oxidation state +2, the electronic configuration is 3D8 4s0. 3D8 4s0 and 4p0. Now let us see here 3D8. So 3D subshell 8 electrons are present. 1, 2, 3, 4, 5 orbitals I am taking here. 1, 2, 3, 4, 5, 6, 7, 8 and 4s is 1 empty orbital. 4p also 3 empty orbitals are present in the 4p. Now here cyanide is what? Strong field ligand. We know that in the primes are strong field ligand, unpaired electrons are going to be paired. So now this unpaired electron what happening here? Paired. So with now the total electrons how many here? There is no change in the total number of electron. The total number of electron will be same, but it will be paired. 1, 2, 3, 4, 5, 6. This electron is coming here. 7, 8. So now here one empty orbital is present in the D subshell. So one empty orbital here and here what is the cyanides? How many? 4. So number of ligands is 4 and number of electron pairs donating to the central metal atom also what? 4. Because cyanide is monodentate ligand. So it means it donate only 1 electron pair. Totally such type of ligands are 4. It is donating the 4 electron pairs to the nickel. At that time the nickel coordination number is 4. So according to valency bond theory, nickel it is makes the 4 available empty orbitals is equal to its coordination number. So one available empty orbital in the s orbital also one available empty orbital, and the totally p orbitals are 3, but we need only 4 available empty orbital, one orbital from the d, one orbital from the s, and 2 orbital from the p. So totally the hybridization of the complex is what here, dsp2. dsp2. So here once you see here also 4 available empty orbitals, here also 4 ligands, here also 4 ligands, but the what here hybridization is sp3, their hybridization is what, dsp2, right? So depend on the what here number of unpaired electrons are pairing here, okay? Depend on that what here hybridization will be changed. So in this complex the hybridization is dsp2. Next of all, here geometry is what, hybridization if it is sp3, the geometry is tetrahedral. If the hybridization is dsp2, the geometry is a square planar. The geometry is what here, square planar. So geometry is square planar. So next of all, magnetic moment or spin multiplicity. Spin multiplicity nothing but what is the formula, 2s plus 1. S nothing but a number of unpaired electron. Is any unpaired electron is there? No. That means 2s nothing but s value 0. Finally 2 into 0 plus 1 totally 1. The spin multiplicity is 1. Next of all, magnetic moment. Magnetic moment nothing but root over n into n plus 2. So root over n into n plus 2 nothing but n nothing but number of unpaired electron. There is no unpaired electron. At that time magnetic moment also 0. And here all are paired of electrons, so that means this is what, diamagnetic in nature. This complex in which nature? This complex is in a diamagnetic in nature. So this is about what, nickel Cn4. Okay, so this is the two different complexes. This is the two different complexes, and we are identifying the what here, hybridization, geometry, and spin multiplicity, magnetic moment, and magnetic nature according to this theory, according to valency bond theory. Right. So this is that. Here once you can identify, right? So this is that, right? So completely. So next one is some exceptions are there here. Some exceptions are there in the valency bond theory. So what is the exceptions? Let us go into discuss now. Right. So the another example is nickel PpH3 taken twice and Cl2. Right. This is the complex. To this complex we have to identify the geometry and hybridization of this complex. Here PpH3 taken twice. So this is a neutral molecule or neutral ligand. So this is what, neutral. Okay, this is a neutral ligand, and chlorine we know that a negative ligand, right? So now let us see that nickel. Here chlorine is -2 and it is a neutral, and this is a -2 nothing but the nickel charge will be +2. So nickel oxidation state is +2. Nickel oxidation state how much here? +2. So nickel oxidation state +2 nothing but electronic configuration of the nickel as per the oxidation state 3d8 4s0. 3d8 4s0 and 4p0. Right. So now let us see here 3d8 4s0 and 4p0. 3d8 electrons are present. So now here these 8 electrons are 1 2 3 4 5 6 7 8 electrons are present. In the 4s there is no electron, and 4p also there is no electron. Right. So but here what happened, this is the chlorine is a weak field ligand, and this PpH3 is a strong field ligand. This is what a strong field ligand, neutral and strong field ligand. Neutral and strong field ligand. So we know that in the presence of strong field ligand, unpaired electrons are going to be paired. But here what happened, due to the bulky size of the PpH3, due to the bulky size of the PpH3 ligand, these unpaired electrons are not going to be paired. These unpaired electrons are not going to be paired. Let us see here. This is the nickel, and 2 chlorines are present here, and 2 bulky groups of PpH3 present here. So this is the 2 bulky groups are PpH3, and this is the 2 bulky groups of the PpH3. So this is the bulky size of the PpH3 groups. That unpaired electrons are not going to be paired. These unpaired electrons are present as unpaired electrons only, right? So at that time, here what happened totally, so this PpH3 neutral and monodentate ligand, that means it can donate the 1 electron pair. Such type of ligands are 2. So PpH3 is monodentate ligands are 2. Chlorine also monodentate ligand, this type of ligands also 2. So totally, what here monodentate ligands, how many? Totally 4. That means these ligands are donating the 4 electron pairs to the central metal atom. So now 4 electron pairs are donating the central metal atom. That means central metal atom, what coordination number is 4. 4 electron pairs are donating by the ligands to the central metal atom. Because of that, central metal atom coordination number how much here? 4. So now we know that according to valency bond theory, central metal atom makes the available empty orbitals, it is equal to its coordination number. Now nickel coordination number how much here? 4. According to the coordination number 4, it will make the 4 empty available orbital. The 4 empty available orbital, 1 orbital is S and 3 orbitals are the P. So totally how many empty orbitals are possible? 4 sp3 empty orbitals are possible. Now the hybridization of this complex is what here? sp3 hybridization. right? So hybridization is sp3. Okay, hybridization is what here? sp3. Next of all, geometry. What's the geometry of the complex? Hybridization sp3 nothing but the geometry is tetrahedral. Geometry is what here? Tetrahedral. Next of all, what? Spin multiplicity. What is that? Next of all, spin multiplicity. What is the formula of spin multiplicity? 2s plus 1. S nothing but number of unpaired electrons. So how many unpaired electrons are present? 2. Each electron spin value how much plus of? So 2 electron nothing but 1. So S value is 1, 2 into 1, 2, 2 plus 1 is equal to what? 3. So the spin multiplicity is what here? 3. Next of all, what here? Magnetic movement. Next of all, what? Magnetic movement. Magnetic movement formula is what? Root over n into n plus 2. Root over n into n plus 2, nothing but n indicating what? Number of unpaired electrons. How many unpaired electrons are there here? 2. So 2 unpaired electrons, nothing but root over 2 into 2 plus 2. 2 plus 2, 4 and 4 into 2, 8. So totally that is what? Root 8. Now here how many unpaired electrons are there? 2. Okay, not only 2, even 1 unpaired electron also there. We can consider the nature of the complex is paramagnetic. So finally this is the paramagnetic complex. What is the nature of the complex here? Paramagnetic. So this is the paramagnetic nature. Okay, this complex is which nature? Paramagnetic in nature. And the hybridization is what? sp3 hybridization. Geometry is what? Tetrahedral. Spin multiplicity 3 and the magnetic moment is what? Root 8. So this is the what? One of the limitation or one of the exception. One of the exception of the valency bond theory. What is the exception? Even though strong field ligand is present here, unpaired electrons are not going to be paired because of the bulky size of the ligand. Because of the what? Bulky size of the ligand. So this is one of the exception in the valency bond theory. Right. Let us see with another exception of the valency bond theory. Ruthenium, PPH3 taken twice and Cl. So this is the coordination complex. Now let us see that what type of hybridization is possible here. So now here PPH3, as per what we discussed previous, it is a neutral ligand and chlorine is a negative ligand. Right. So chlorine negative ligand nothing but this is a -1. At the same time, the ruthenium oxygen state will be +1. Ruthenium oxygen state will be +1. And ruthenium is a large metal here. Ruthenium is what here? Large metal. So ruthenium is a large metal. Not only ruthenium, platinum, palladium, ruthenium, right? So platinum, palladium and ruthenium like large elements or large metals. Ruthenium, platinum, palladium, such type of large metals is present. These large metals can arrange the large ligands on the plane. These large metals can arrange the large ligands on the plane, right? So that means here totally number of ligands, how many? 4 ligands is present. So generally when the 4 ligands is present, we are expecting the 2 types of hybridations. One is sp3 hybridation we can expect, one more is dsp2 hybridation we can expect. sp3 nothing but here what is that geometry of the complex? sp3 nothing but the geometry is tetrahedral and dsp2 nothing but the geometry is square planar. The geometry is what? Square planar. So these 2 hybridations are possible when the coordination number is 4. When the coordination number is 4. So if you see that here ruthenium coordination number is 4, how can you say the ruthenium coordination number is 4? So PPH is neutral ligand but monodentate ligand. Such type of monodentate ligands are 3. That means PPH3 donating 3 pair of electron, 1 chlorine donating 1 pair of electron. So totally 4 electron pairs are donating by the ligand. So to the central metal atom. At the time coordination number of the central metal atom how much here? 4. So coordination number nothing but how can you say that coordination number? Definition here. So number of electron pairs donating by the ligands to the central metal atom is called coordination number of that metal. Coordination number of that metal. So here totally 4 ligands are donating the 4 electron pairs to the central metal atom. At the time coordination number of the central metal atom is 4. Now coordination number 4 nothing but 2 types of hybridations are possible. sp3 hybridation is possible and dsp2 hybridation is possible. sp3 hybridation also possible. At the same time which hybridation is possible? dsp2 hybridation also possible. So now when the sp3 hybridation is possible, the geometry of the complex is tetrahedral. When the dsp2 hybridation is possible, the geometry of the complex is square pyramidal. So sorry, square planar. Now let us see in these 2, okay, which one is follows this one. But here you see that ruthenium is what? A large metal. Okay, ruthenium like platinum like palladium, such type of large metals if it is present, and this is the what? Bulky size of group. Before we discussed, this is the bulky size of the group, right? So when the bulky size of the group is present, before the example the hybridation is sp3 hybridation, but the same bulky size of group is present, but before that nickel is the what? Central metal atom, but here ruthenium is the central metal atom. Compared to nickel, ruthenium is the large metal. So because of the large metal present here, these large metals can arrange the what? Large ligands on the plane. At that time it will be give the square planar structure. But small ligands cannot arrange the large ligands on the plane. That's why it is not given the square planar structure. Because of that, in the previous example, that does not given the square planar structure. Which structure is given? Tetrahedral structure is given. Because of that, nickel is a small central metal atom, but PPH3 is a large ligand. So the small metal cannot arrange the large ligands on the plane. Only the large metal can arrange the large ligands on the plane. At the time, square planar structure is possible. Right. So because of that, a square planar structure is possible. So we can say that what is the hybridization of the complex here, DsP2, and the geometry of the complex here, what? Square planar, we can say that. So actually what we are expecting, we are expecting as a sp3, but here possible is what? DsP2. So this is one of the exception, right? So one more I can explain here. If you take the nickel, what we are taking? Nickel. So the central metal atom we are taking as a nickel, and here we are taking that PPH3 2 and Cl2. So totally here also how many ligands is present? PPH3 2 ligands, chlorine also 2 ligands, totally 4 ligands is present. But here what happened? Central metal atom is what? Nickel. So nickel is a small central metal atom. The small central metal atom cannot arrange the large ligands on the plane. At that time, does not give the planar structure. It will give the which structure? Except the planar, remaining structure is what? Tetrahedral. So it will be given the tetrahedral structure. Because of how many ligands are present? 4 ligands are present. Here also 4 ligands, here also 4 ligands, but it is giving the square planar, it is giving the tetrahedral due to the central metal atom. Central metal atom, if it is large, it can arrange the large ligands on the plane, but small central metal atom cannot arrange the large ligands on the plane. Because of that, it is a tetrahedral and it is a square planar structure. So this is a very important one of the exception in the valency bond theory. Right. So let us discuss that. Next one is ligands. So starting we discuss the ligands are 3 types. One is a strong field ligand, and one more is weak field ligand, one more is average ligand. Now average ligands, what we discussed, average ligand sometimes is act as a strong field ligand, sometimes act as a weak field ligand, depend on the central metal atom. Now let us see, for example, ammonia. So ammonia is acting as a average ligand. What we given the starting class strong field ligand, average ligand, weak field ligand. In that we given the NH3 is average ligand. So average ligand NH3, it is act as a strong field ligand, weak field ligand, depend on the central metal atom. So at what conditions it acts as a strong field ligand, at what conditions it acts as a weak field ligand. That means at what metals, in the presence of which metals it acts as a strong field ligand, which metals act as a weak field ligand, let us see. So ammonia acts as a strong field ligand in the presence of cadmium, in the presence of cobalt, in the presence of iron, in the presence of copper. So in the presence of these 4 metals, the ammonia is acting as a strong field ligand. In the remaining all the metals, in the case of remaining all the metals, the ammonia acting as a weak field ligand. The ammonia acting as a what here? Weak field ligand. So now let us see, based on this, we will see some examples according to valency bond theory. So now, according to this explanation, one of the complex is FeH2O6. What is that here? FeH2O6. FeH2O6, right? So FeH2O6 plus 3. Okay, ammonia is a weak field ligand. Sorry, water is a weak field ligand here. So in the presence of weak field ligand, unpaired electrons are never it will be paired, right? And water is a neutral ligand. What is what here? Neutral ligand. In the case of neutral ligand, there is no change in the oxidation state, but here plus 3 is present. So this plus 3 belongs to iron. Now iron oxidation state how much here? Plus 3. Iron oxidation state how much here? Plus 3. Now iron atomic number is what? 26. From the 26, so that means 3d 6 times 4 is 2. Iron losing the 3 electron, 2 electron from the 4s, 1 electron from the 3d it is losing. Now how many electrons in 3d? 5 electrons in 3d, 0 electrons in 4s. 5 electrons in 3d and 0 electrons in 4s. Now let us see here, H2O is a neutral ligand and it is a weak field ligand. 1, 2, 3, 4, 5 and s orbital, and next of all p subshells are how many? 3. So now next of all d also, 4d also positive. 1, 2, 3, 4, 5. Now in 3d how many electrons are present? 5 electrons is present. 1, 2, 3, 4, 5 and H2O is a weak field ligand. In the presence of weak field ligand, unpaired electron never it will be paired. But here what? How many ligands are present? 6 ligands are present. Water is monodentate ligand. That means it can donate the 1 electron pair to the central metal atom. Such type of ligands are 6. That means 6 electron pairs donating to the iron. So number of electron pairs, how many donating to the central metal atom? 6 electron pairs are donating to the central metal atom. That's why the coordination number of the iron is 6. According to valency bond theory, so the central metal atom makes the available empty orbital is equal to its coordination number. So according to this explanation, iron coordination number is 6. It will be make the 6 empty available orbital. 1, 2, 3, 4, 5, 6. 1 s orbital, 3 p orbital, 2 d orbital. By this combination, the hybridization is possible sp3d2. What the hybridization is possible here? sp3d2 and all are unpaired electrons. So that's why the magnetic nature is what? Paramagnetic nature. Next of all, spin multiplicity. What's the formula of the spin multiplicity? 2s plus 1. S nothing but number of unpaired electrons. How many unpaired electrons are present? 5. 5 unpaired electrons nothing but each unpaired electron or each electron value is what? Half. So totally 5 electron nothing but 2 and half. Then 2 into 2 and half is equal to 5. 5 plus 1 is equal to what? 6. So the spin multiplicity is 6. So next of all what? Magnetic movement. Magnetic movement formula is what? Root over n into n plus 2. N nothing but number of unpaired electrons. Unpaired electrons how many? 5. Then 5 plus 2 7. 7 into 5 what? 35. So root over 35. Okay, so and next of all sp3d2. Totally how many orbitals are, how many ligands are present? 6 ligands are present. 6 ligands nothing but only one type of hybridization is possible. The hybridization is octahedral. What's the hybridization of the complex here? Octahedral. So hybridization of the complex is octahedral and the geometry is octahedral and the hybridization is sp3d2 and magnetic nature is paramagnetic and multiplicity, spin multiplicity is 6 and the magnetic moment how much here? Root over 35. So this is the what characters for this complex. Now let us see with another example. Right. Let us see the next example. CONH3 6 and plus 3. Right. So for this complex you have to find the hybridization and geometry. As per what we discussed the previous, NH3 is act as a strong field ligand and weak field ligand, but is dependent on the central metal atom. So what is the central metal atom? Is a cobalt. So central metal atom, when it is cadmium, when it is cobalt, when it is iron, when it is copper, in this presence of these four central metal atoms, the ammonia acting as a strong field ligand. So here CO is a cobalt. So in the presence of cobalt also the ammonia acting as a strong field ligand. The ammonia is what here? Strong field ligand. So the presence of strong field ligand, what happens? Unpaired electrons are going to be paired in the presence of strong field ligand. Now let us see. Here ammonia is a neutral. So neutral does not have the charge and the complex plus 3 charge belongs to now cobalt. Right. So the oxidation state of the cobalt how much here? Plus 3. Oxidation state of the cobalt how much here? Plus 3 and the cobalt atomic number is 27. So now electronic configuration of the cobalt how much here? 3d7 4s2. 3d7 4s2 cobalt. Now cobalt plus 3, that means cobalt losing the 3 electron. 3 electrons, but 2 electrons from the 4s, 1 electron from the 3d. So that means 3d 6 electrons are present and 4s 0 electrons are present. That means the configuration is 3d 6, 4s 0 and 4p 0. Now let us see here 3d 6. 3d 6 nothing but in the d subshell 6 electrons are present here. 1, 2, 3, 4, 5, 6 and 4s 0 electron is present and 4p also 0 electron is present. But here ammonia acting as a strong field ligand. In the presence of strong field ligand, unpaired electrons are going to be paired. So how it will be paired? So this electron is going to be paired here and this electron is going to be paired here. At the time this electron is coming and pairing here, this orbital is empty. Like this electron coming and pairing here, this orbital is empty. Totally 2 d orbitals are empty. Total how many d orbitals are empty here? 2 d orbitals are empty. 1, 2, 3, 4. So totally what? 2 d orbitals are empty. So 2 d orbital is empty. 1 s orbital also empty and 3 p orbitals also empty. Now let us see the coordination number of the what? Cobalt. Coordination number nothing but what? Number of electron pairs donating to the central metal atom. So ammonia is the monodentate ligand. It can donate only 1 electron pair. Such type of ligands are 6 is there. That means 6 electron pairs donating to the cobalt. Now cobalt oxidation number cobalt coordination number how much here? 6. So according to valency bond theory, coordination number of the cobalt is 6. That means the cobalt is makes the available empty orbitals equal to coordination number. What is the coordination of the cobalt here? 6. That means it will be make the 6 empty orbital. So what is the 6 empty orbital? 2 orbital from the D, 1 orbital from the S, 2 plus 1 3 and 3 p orbital. So total 6 empty orbital. Now by these intermixing, the hybridization of this complex is what? D2sp3. What's the hybridization of the complex? D2sp3. Whatever the hybridization, if the ligand 6 is present, the geometry of the complex is octahedral. The geometry of the complex is what here? Octahedral, and there is no unpaired electron. There is no unpaired electron, but magnetic moment will be 0. Magnetic moment is what here? 0. Right. So there is no unpaired electron. That's why magnetic moment is 0. All are paired electron. All are paired electron, but there is a diamagnetic in nature. What is the nature here? Diamagnetic in nature. Right. So next of all, spin multiplicity. So all are unpaired electron. There is no unpaired electron. That means S value is 0. S value is 0, nothing but spin multiplicity is what? 1. Spin multiplicity is what? 1. So the hybridization is D2sp3. Hybridization is D2sp3, and the geometry is octahedral. and the magnetic nature is diamagnetic, spin multiplicity is 1, and the magnetic moment is 0. Right, so this is the what NH3. In the case of NH3, what it is present with the cobalt. So cobalt, what in the presence of cobalt, ammonia acting as a strong field ligand. But the same NH3, if it is present in the presence of water, another ligand, sorry, another central metal atom, maybe the NH3 acts as a weak field ligand. For example, nickel you take. In the presence of nickel, the ammonia acting as a weak field ligand. Right, so only the ammonia acting as a strong field ligand in the presence of cadmium, cobalt, iron and copper. In these presence of 4 metal atoms only, the NH3 acting as a strong field ligand. In the remaining cases, the NH3 acting as a weak field ligand. So this is the session, and we will discuss the another topic in the next class. Thank you.